Interaction term. We already seen the interaction term in the categorical variable. This is what we call the interaction term. Right? So x and x times 2. x1 times x2. When we have to have the interaction term is the when x1, effect of x1 is the different when x2 is exist or when x2 doesn't exist. So doesn't matter what is x2, x1's effect is always the same, then we don't need to include the interaction term. But sometimes effect of the x1 is that depends on the what x2 is. Sometimes something is not effectively working, but when the other thing is work together, there can be a synergy, and then the effect of x1 can be totally different. So when you think or you observe the kind of the possibility, effect of x1 can be different when x2 exists or not, then you think about the interaction term x1 times x2. So basically, you will see the beta 1 is the when this is a x1's effect of x1, when this is not exist, when this is x2 is 0. x2 is 0, this is gone, this is gone. So this is a purely x1's effect on the y when x2 is 0. And these together will be the x1's effect on y because the when x2 is 1. When x2 is 1, this is a beta 1 x1 plus this beta 2 will be go to the, because this doesn't have x2, this will be a part of the interception, and x2 is 1, then this also will be the x1's effect, so it will be the beta 1 plus beta 3. Or if x2 can be not only a 0 or 1, if there is something, and altogether this will be the effect of x1 when x2 is not 0. x2 is not 0. Okay, so clearly x1's effect on y is different, depends on the x2 exists or not. So in that case, we have to consider the interaction between x1 and x2. Okay, clearly this is the, if x1 and x2 is the binary variable, then you can see that our regression formula is totally different, but this is a effect of x1 and this is a effect of x1. Depends on the x2 exists or not. So we have a one regression model, but actually this one contains the two different versions. This is the example of interaction. So effective expose index. So this is like when you do the advertising. So effective expose index is the how many people actually recognize our advertisement. So this is not the directly, but this is directly related to the how many item you're gonna sell, because if you don't, the customer doesn't recognize our advertisement, actually the advertisement effect will not be there at all. However, effectiveness of the exposure is the how much customers actually recognize our advertisement. So this number, higher the better, more effect, but how much money we spend. So obviously you spend more money, you can have a higher effective exposure index, but that effect of the money will be different, depends on the type. Here the type is, this is the magazine. This is newspaper, right? So sometimes you spend a lot of money on the newspaper that doesn't have a exposure index that much, but on magazine you can have a lot, or vice versa, right? So if effect on the $1 or more will read how much more the exposure index will be different between the newspaper and the magazine. So we want to actually we can create the two separate regression model, money effect on the exposure index on magazine and on newspaper, but we can combine together and then create the one regression model using the interaction term. Okay, so as you can see, the R square is pretty high. Everything is significant, right? So everything is significant. So you can tell this is like a y equals, this is 76. Yeah, I have the equation here. Y equals 76.7 plus 1.07 cost minus 213 type plus interaction term. This is interaction term. So actually you can separate out what is our regression for newspaper and this is for the magazine. So it's totally different, right? However, we combine these two cases into the one regression equation. Transformation. We already seen the transformation because we already seen when we can apply the log on the y or log on one of the x variable. So this transformation is when you see there is something non-linear relationship between these two, then we can change. So square root transformation is you just apply the square root either on the y or on x. Logarithm is you just apply the log or natural log. Reciprocal is the 1 over x or 1 over y, and the exponential is the exponent to x or exponent to y. So actually to find out we have to do the square root transformation, or we have to do the log transformation, we have to do the reciprocal transformation, or exponential transformation. This is not clear. That's why some people said this transformation, I mean model selection, what kind of model should we use for the regression? That's kind of the art. Of course, we have a technical part here, so that's why the people said this is like a science and art together. So you should not looking for some specific precise step or the procedure. Actually, sometimes you have to rely on your like feeling or your idea or that's why sometimes we just ask which variable should we use to the just expert without seeing the data. So roughly we want to get an idea here. So logarithm transformation. Actually, log transformation can be applicable to the y variable also. But when you see the graph, when you can simply plot the graph y versus x1 or y versus x2, if dotted line show up to this shape or this shape, then you have to think about the log. And also, when the dotted line have this kind of shape, is getting bigger and bigger outside, but it's tiny in the inside, then you better try the log. Reciprocal is similar, but if there's clearly the asymptote here, it's getting close to this line, asymptote. If there is a clear asymptote, then you have to try the reciprocal. what's the difference between this one and this one? This one doesn't have asymptote here. You can keep going up. However, this one has a clear asymptote. Then you better, you should try the reciprocal. Again, there's no clear line when you have to use a reciprocal, when you have to use a logarithm transformation. That's why it's also part of the art, so you have to find out. But the difference between the logarithm and reciprocal is looks like there's asymptote or not. Exponential transformation is different, right? So this model is something like this. So you will see this exponential transformation later, another chapter, but this and this are the equivalent. If you apply the log onto only the y variable, that's the same as you're applying the exponential on the independent variable side. So whenever you plot the graph, and then you find out that this kind of relationship is not clearly linear, then you can choose exponential transformation. Again, there's no clear rule which transformation we should use. So yeah, I'm just trying to tell you this is possible method and that is possible method. We cannot say that transformation is better than the other transformation clearly, unless we have some clear target. I mean, I'm trying to maximize my R square. Then yeah, clearly then you can try all possible things. Then choose the highest R square. Otherwise, however, when you just say the good model, we cannot tell which one is better. It's not that simple. The reason is as you add more and more variable, actually your R square will go up just a little bit. Even if it's just a little bit, it will keep going up. So then I have to put all the possible variable in it. That's a good model. That's not. We better have a smaller the variable as less as possible. And also we want to increase our R square as much as possible, but both of them have to be achieved. We will talk about it later in this class.